right now, starting the recording now, right? So question one, figuring out oxidation state, right? Figuring out how to assign oxidation state. So yeah, the exam's all multiple choice, right? It's gonna be the same format as exam one. Yeah. So the first one, calcium sulfide, right? You know, calcium is group 2, right? I'm sure everyone has handy little periodic table clip art there. So calcium being group 2, right? Everything in group 2 is going to have a 2+ charge. So in calcium sulfide, right? Calcium is 2+. That makes sulfur 2-, right? Sulfide. For the sodium azide or sodium nitride, sorry, sodium is group 1, so sodium is always going to be +1. So the total charge there is 3+. This needs to be neutral, right? When I add these two together, it needs to be neutral. So that means nitrogen, right, needs to be 3- to balance that out. For the magnesium sulfite, right, magnesium is group 2, so it's 2+. That makes the sulfite 2- to balance that out. But it's asking for the atom with the highest charge. So we need to assign a charge to sulfur and oxygen as well. So to break up sulfite, right, all we have to do is break this down and say, okay, I've got sulfur, I've got 3 oxygens. The total charge is -2. And I know that sulfur, right, sulfur is always oxygen is always 2-, right? So 3 times 2, that's -6. So I've got -6 charge from oxygen. To balance that out, sulfur needs to be 4+. All right, we'll do the aluminum nitrate, right? Same thing. Aluminum is group 3. It's always going to be 3+. So aluminum 3+, or this is nitrite rather, NO2 -1. We can do the same thing and break down nitrite. NO2 -1, we can break that down into nitrogen, 2 oxygens. Again, the total charge needs to equal the -1. Oxygen is always -2, so 2 times -2, that's -4. So nitrogen needs to be 3+ in that case. The ammonium chloride, right? Ammonium is NH4+. The chloride is -1. And then again, if we wanted to figure out the charge, right, we can break down the ammonium as well. All right, ammonium, NH4. I've got nitrogen, I've got 4 hydrogens at +1 each. So that's a +4 charge. The whole thing is +1 overall. So nitrogen needs to be 3- in ammonium for that to balance out. So looking at all the charges, right? Magnesium sulfite, I have sulfur at 4+. That's the highest oxidation state of all of those available. Sorry, I missed a bunch of questions evidently. Yeah, so Maya, when sulfur is an ionic compound, yeah, sulfur will always be -2 in an ionic compound. However, sulfite, right? This sulfite is nonmetal with nonmetal. So we're going to have to assign a charge to sulfur there in this molecular compound. In an ionic compound, yes, sulfur would always be 2- because it's the same group as oxygen, right? But in a molecular compound, the rules are a little bit differently. The reactivity is a little bit differently. Yeah, and then Will, right? The magnesium is 2+. Because sulfite is 2-, right? Correct, yeah. Sophie, I'm doing algebra to figure out the unknown charges. I'm sorry, I'm just catching up with all the statements here. Does it matter if it's 4 plus or 4 minus to be the highest, like absolute value? We don't have anything at 4 plus, right? So, right, this is the largest number, so yeah. Mia, all right, I'm sorry, you know? Again, don't do the direct messages because everyone needs to see these questions. Otherwise, I'm just reading them to myself, right? So Ravi, sodium has an oxidation state of +1. Where are you seeing sodium at +3, right? So up here, I think you're seeing, I've got 3 sodiums at +1 for a total of +3 total, right? Mia, all right. And then is this based on, yeah, again, it would just be the largest number. I'm not going to give you one where you have two, that one's +4, one's -4. You'd have one that's just the absolute value. Absolute, what's the largest oxidation state? What's the largest charge? Yeah, Robert, we're just kind of assigning a charge to it. It's more of an oxidation state. It's not a formal charge. And yeah, we'll do redox reactions. So I think I got everyone's question just from question 1. And the question, can the question transform to highest reduction number? No, right? It would be the same question, right? We're just looking for the highest assigned oxidation state, whether it's positive or negative. Yeah. The oxidation number of calcium sulfide itself, right? So calcium sulfide itself, and this is going to help us with redox reactions, right? Calcium sulfide together needs to be 0, right? The total charge on calcium sulfide needs to be 0. It is 0 because in that ionic compound, right, calcium is 2 plus and sulfur is 2 minus. Does that answer your question, Candace? Yeah, hopefully we're just going to screenshot the Mia, not Maya. I'll keep that. Oh, all right. Question 3, I think, is next. And yeah, so here's a redox reaction, right? In which of the reactions does the oxidation number of hydrogen not change? And I think I've pronounced your name wrong all semester. So yeah, I don't know. Once it gets stuck in my head one way, yeah, you do. You correct me every class. I know, but it just, for some reason, it's like stuck in my head that way. And so, yeah, I don't correct anyone when you misspell my name or all the different things that come my way. In which reaction does the oxidation number of hydrogen change? So one key thing to like pick out a redox reaction is happening is that we have something that's a solid going to something that's aqueous, because any pure elemental solid, right, needs to have an oxidation state of 0. So sodium is 0 as solid sodium. If we look over here in sodium hydroxide, all right, now I've got sodium +1 because hydroxide is -1. So the oxidation state of sodium has changed. And then if I go and take a look at water, we can break apart water. I've got 2 hydrogens at +1 each, so a total charge of +2, and then an oxygen at -2, right? So water is neutral there, but hydrogen is +1. And again, any diatomic, right, any molecule also is going to have a 0 oxidation state because it comes together to be balanced. So hydrogen, just H2, is neutral. Here, I can't assign, right, if I've got 2 hydrogens in H2, I can't say one hydrogen is +1 and one hydrogen is -1 because they're the same element, right? It doesn't make any sense to assign one +1 and one -1. So that makes the whole thing 0. We're just not going to assign a charge to hydrogen. We're just going to say it's 0. So it's the second one here, right? It's choice B. That's a redox reaction, right? None of the other reactions are redox reactions. Nothing else we could go through, break them apart. We're not going to see the change in the oxidation state. So correct, right, Alexander, right? And that's a good key that you've got a redox reaction is that you have a pure elemental solid becoming something aqueous in solution. Yeah, any elemental solid, the only things that should have charge are aqueous, right? Because that means they can be in solution as ions, and our ions are what are charged. So if it's a solid, if it's a liquid, it's a gas, the charge should be 0, right? It should be neutral. D is not the answer because if we go and look here, hydrogen is +1. If we ionize that acid, hydrogen is +1. And if we break apart water, right? Hydrogen, I've got 2 hydrogens at +1, and I've got oxygen at 2-. So D is not the answer because hydrogen is +1 here, and it's also +1 here. And when I said solids, liquids, and gases need to be neutral, it's the whole compound, right? So all of water needs to be neutral. All of this acid needs to be neutral. That being said, it's aqueous, so we can split it into ions and say the hydrogen's +1, right? The chloride's -1. We can, just like we can split apart this water to assign those charges. So that's why D can't be the answer. Correct, right? So Sophia, insoluble compounds are going to be our solids. They're going to be a precipitate. If they're ionic and they're soluble, they're going to be aqueous, right? If they're molecular and soluble, they're just going to be like a molecule in solution, right? So like sugar and water. Oxidizing agent is what causes oxidation, right? It itself gets reduced. The reducing agent causes reduction. It itself gets oxidized, right? If something is paired in the reactants and ends up alone in solution, like this example, does that mean the oxidation number changed? Yeah, Will. That's kind of what I'm saying by identifying sodium solid by itself, and then all of a sudden it's aqueous with something else. That's a good sign that a redox reaction took place. Yeah. All right. I think I got all those questions in. See anything from Mia? Mia, anything? We're good. Not this example, but in general, why does chlorine have a charge of -1 and not 0? Diatomic chlorine, we would call diatomic chlorine also 0. We would call it 0 as well. Just like we call H2, hydrogen gas, as 0. So Cl2 would be 0. And we would say there's no charge there because I can't see one. We can't assign one chlorine as negative and one chlorine as positive. During the chem tutoring tonight, she gave an example where there was oxidation but not reduction. They both have to occur simultaneously, right? If something is being oxidized and losing electrons, something else needs to be reduced and gain those electrons. So maybe she didn't identify the redox reaction properly, but they both have to happen concurrently. Yeah. All right. Question 5. Definitely. Yeah, well, I've got my PhD in chemistry, and I'm gonna say that if there was if there was oxidation, there needs to be reduction, right? Okay, so the example Mia was, let me just insert a new slide here. I mean, Matt, it's a good question, right? If people are confused, it doesn't hurt to go over it, right? Because that's what they're here for, right? Arsenic plus 3 chlorines goes to 2 arsenic. Let's see, to balance that out, I think it has to be arsenic 3, right? Yeah, I think it was arsenic trichloride, right? Okay, so arsenic is 0. Chlorine is 0 as well. In arsenic trichloride, when we break this down, right, the whole thing needs to be 0 together. But if we were to separate this out, right, arsenic and 3 chlorides, chloride is always -1 each. So I'd have a -3 charge there. That means for this whole thing to have a 0 charge, arsenic needs to be 3 plus. So if we look at the half reactions, right, I'm going to have 2 arsenics go from 0 to 2 arsenics that go to 3 plus. And yeah, just like Sophie said, right, we'll do that by 6 electrons have to be transferred, right? So that's our oxidation half reaction, which makes our reduction half reaction, right? I've got 3 chlorines that are 0, right? Diatomic chlorine is 0. It can't have a charge. It's a neutral molecule, right? It reacts to form neutral chlorine. And then that forms, right, 6 chlorines at -1 each. So how do I balance that out, right? How do I balance that out? The 6 electrons that were lost from arsenic, right, are gained by that chlorine, right? So there is our reduction half reaction. So yeah, Cl2 can't have a minus charge. It's neutral, right? It's a molecule of chlorine gas. Yeah. Right. So absolutely, if reduction is taking place, oxidation needs to be taking place. And vice versa. If something's being oxidized, something needs to be reduced as well. I'll try to post the recording later on tonight. We'll see what I have time for, but I'll post it in the Discord first. If I have time, I will email it out on Blackboard. I'll post it on the Discord server first, though. Yep. Yeah, why is it 6 electrons, right? Because here I've got arsenic is neutral. I've got 2 arsenics at 0. So my total charge is 0. Here I've got 2 arsenics at 3 plus each. So the total is 6 plus. I can't create or destroy charge. I have to have, I can't create or destroy charge. So if the left side is neutral, the right side needs to be neutral as well. So if this is +6, I need to have 6 electrons to cancel that out. Yeah, I have to make a new invite link for the Discord server. The one I made was only good for 7 days. So if you want a new invite link for the Discord server, just send me an email. I'll make a new link and I'll send it out. So are we good with this question now? All right. I know Matt Pinto is. He's ready to move on. All right, question 5. And I'm sorry that the tutoring wasn't, I mean, I don't hire the tutor, I don't train the tutor. But reduction reactions, they happen simultaneously. All right. If I've got 25 grams, and can someone just check this real quick? Do you have 25 grams, or is the mass different? Yeah, it's 25 grams. All right. I'm sorry, Jack. I'll try to keep it back on track. All right. 25 grams of chlorine, right? This thermochemical equation tells us for every 1 mole of chlorine, that's the energy that we release, right? So we can't do anything with grams. We need to convert it into moles. All right, 25 grams. So I know for 1 mole of chlorine, right? Chlorine is 35.45, so 70.9 grams of chlorine. All right, so 25 divided by 70.9. I've got 0.3526 moles of chlorine. Now I go to that thermochemical equation, right? 0.3526 moles of chlorine. I know for every 1 mole of chlorine, right, we're going to release 186 kilojoules. And because it says heat released, that's already kind of telling us, right? It should be a negative number, but right, that takes care of the negative for us, basically. Right, so we multiply by 186, and I get something like 66 kilojoules of energy are released from this reaction, right? I got the 70.9 right here. This came from the periodic table because chlorine equals 35.45 grams per mole. So that means diatomic chlorine, I'm going to have 2 chlorines. So 35 times 2 is 70.45 times 2 is where the 0.9 comes from. Yep. All right, let me do question 9. I think that's up next. Oh, okay. All right. Yep, we're going to get to 24. We got 23 and 24 on the list. So for question 9, 16 is there as well. I mix together manganese, fluoride, and I mix that with silver nitrate. Both of those are aqueous. Both of those are aqueous, right? My 2 possible products. I can make 2 possible products there. Right, one product, I'm going to pair the inner and the outer, right? The outer and the outer, and the inner and the inner. So one possible product is manganese nitrate, and the other possible product is silver chloride, right? From there, we want to just go to the solubility table and look up which one is insoluble, right? We go to the solubility table real quick, somewhere here. Solubility table. My 2 choices, the 2 things I wanted to look up were manganese 4 nitrate and silver chloride, right? I go and take a look. Nitrate is always soluble, right? So the manganese nitrate is not going to precipitate. I look up over here, here are the chlorides, right? Chloride will precipitate when I have silver, lead, or mercury in the solution. I've got silver. So the identity of that precipitate, right, has to be the silver chloride. That has to be our solid, and our manganese nitrate will be aqueous, right? Just going to ignore that question, Jack. Correct. I'll give you all the equations, right? I will give you all the equations. The four for the 4 silver nitrates, that's just to balance the equation out, right? Because I had 4 chlorides here, so that means I need to have 4 silvers because they go together in a 1-to-1 fashion. And because manganese is 4 plus and nitrate is -1, I needed to have 4 nitrates to balance that out. So we just did that by balancing the equation. Yeah, thank you, Sophie, for taking care of that for me. All right, question 8 here. Apparently we skipped. Right, your number might be different. The steps are going to be the same. So for question all right, yeah, we can do 16 grams. Let's see, what are we? Question 8 here. All right, let's say we've got 16 grams of water. Right, we can't do anything with that other than to find moles. So I know, right, water is 18.02 grams per 1 mole. So I'm going to have a little bit less than 1 mole of water, right? 16 divided by 18. All right, I've got 0.8879 moles of water, right? If your number is different, you can just plug in your number and do the same steps, right? So take that many moles of water. From there, I'm going to just go to the balanced chemical equation and use the molar coefficients to tell me, all right, for every 4 moles of water in the reaction, I need 5 moles of oxygen. So moles of water cancel out. We're going to multiply that by 5/4. And I get something like 1.10, 1.11 moles of oxygen. From there, I can convert that to mass, right? 1.11 moles of oxygen. And I know for every 1 mole of oxygen, I need to have 32 grams, right? So multiply that by 32. And I get something like 35.5 grams of oxygen. So I would try 2 significant figures, right? And yeah, I think you want to round that up, but in some cases, for some reason, they're not rounding the answer up. So if 36 grams doesn't work, try 35 grams, and that might work for question 8. For whatever reason on the settings, it wasn't rounding it up. Miss Brody, everyone's is different. Everyone's going to have a different number. And yeah, nitrate is always soluble. I'll just call you that from now on in class. All right, question 10 will be the last one for this block. All right, we've got this reaction, the Haber process, right? Nitrogen reacts with hydrogen to produce ammonia. 1 nitrogen, 3 hydrogens makes 2 ammonia. So what's the limiting reagent, right? Well, they react in a 1-to-3 ratio. So this is my nitrogen and this is my hydrogen. So if I need 3 to react, there's 1 reaction. There's 2 reactions. There's 3 reactions, and I have 1 nitrogen left over. So my limiting reagent is hydrogen, right? What I have in the excess is nitrogen. And how many molecules excess do we have, right? I have one molecule of nitrogen left over, right? When all that reaction goes through 3 times, I'm going to have one singular nitrogen left over.